Alright, this is lesson 4.5. It's integration by substitution. Integration by substitution is going to be the process of finding the antiderivative of something that we use the chain rule to find the derivative of it before. So where we use the chain rule and we had an inside and an outside part, now when we integrate by substitution, we're going to be recognizing that we have something that was previously a chain rule to do the process of integration by substitution. So first of all, the first type we're going to use is when you recognize the pattern or recognize that you have a chain. So if you look at the example that we have here, we definitely have a composite function because you have x squared plus 1 to the second power. That's definitely composite. So how you recognize the chain is by looking at this part after it. And so how I can check that is I say, is 2x the derivative of x squared plus 1? And it is the derivative of x squared plus 1. So that means that the 2x is the second part in the chain when we did a chain rule before. And so what that does is it groups the 2x with the dx. The reason that's important is because, when we integrate, the dx goes away. So for this function, to get the answer, we have x squared plus 1 to the second power. Since the 2x is already there and we're grouping it now with the dx, since that's going to go away with the process of integration, x squared plus 1 squared becomes x squared plus 1 to the third power over 3 plus c, which is exactly what you want to be able to do with a grouping of parentheses. And we would have liked to have done it before, but when we tried to do it before, it didn't work out. So if you only have x squared plus 1 squared, you can't do it. But as long as you have that 2x to go with your dx, you can use the same method that we've used before with polynomials. So let's look at some examples and see if we can recognize the pattern. Okay, so trigonometry is one of the types of function that uses the chain rule the most when we do the derivatives. So if we look at this one, and I'm going to rewrite it just a little bit. It's not a big deal if you don't rewrite it. Oh, I'm not doing a very good job there. Let's try it again. It's not a big deal if you don't rewrite it. I just like to do this because it helps me to see what I can actually do with my problem. So I'm going to recognize, is 5 the derivative of 5x? And the answer is yes, it is. So that means I can group my 5 with my dx, and it allows me to immediately integrate this cosine 5x. So if you integrate cosine, you get positive sine. Since this was a 5x, this is a 5x. So cosine 5x becomes sine 5x plus c. Without that little 5 there, we would have had to do a different method to get our integration for this. And we'll talk about that more a little bit further on, or possibly in some of your homework examples that you're going to do. Alright, let's look at another one. This one I want to rewrite it first. So I'm going to rewrite this as x squared plus 4 parentheses to the negative 1/2 power, and then next to that we'll have the 2x and the dx. So let's check. Does this work out? Is 2x the derivative of x squared plus 4? Yes, it is. So we're going to group the 2x with the dx. We know that's basically going to go away. So when we integrate this, x squared plus 4 to the negative 1/2 power is now going to be x squared plus 4 to the positive 1/2 power divided by 1/2 plus c. And then, of course, we know if we divide by 1/2, we can flip that and multiply, and we can put the 2 up here, and we have 2 times x squared plus 4 to the 1/2 power plus c. All right, let's look at another one. Rewriting it first, I'm going to have x squared plus 2 to the 1/2 power, and then x, and then dx. Okay, this one's going to be a little bit trickier because when I say, is x the derivative of x squared plus 2? It's close. What is the derivative of x squared plus 2? The derivative of x squared plus 2 would be 2x, right? So that really needs to be a 2. Well, since 2 is just a constant, and we're just going to put it in the place of a coefficient, I'm actually going to put that 2 right there, and all I'm going to do is balance it outside my integral with a 1/2, because that way if I took half of 2, it would go back to being 1. That's one of those math magic things that you do where you balance the problem by multiplying and dividing by the same number. So now that this does work, 2x dx is together, and that goes away as we integrate. So my solution is going to be 1/2 times x squared plus 2 was to the 1/2 power. Now it's going to be to the 3/2 power, and we're going to divide that by 3/2. But of course, when you divide by 3/2, it really means we're going to multiply by 2/3. So I'm going to put that up here at the front. And I'm going to go ahead and simplify it a little bit. The 2's are going to cancel. So this is going to be 1/3 x squared plus 2 to the 3/2 power plus c. Remember, anytime you don't have numbers on here, you're going to have plus c. So some of these problems will have plus c and some of them won't. Alright, so what did we learn on this one? If we're missing a number, like we were missing the 2, we can put the number in and we can balance it. Okay, so let's look at another one like that. This one goes from 0 to 4, so we're going to be plugging in this time. I have 2x plus 1 to the negative 1/2 power. I don't have to rewrite the 1, so I'm just going to put dx. So now the question would be, really, is dx the derivative of 2x plus 1? Well, the derivative of 2x would be 2. So it would be 2 dx. So I need a 2 in there, so I'm going to balance the 2 with a 1/2 on the outside. So now what I have is 1/2 times 2x plus 1 was to the negative 1/2 power. Now it's going to be to the positive 1/2 power divided by a half, which means multiply that by 2. And then this time we're going to go from 0 to 4. So 2 and 1/2 cancel. So when I go ahead and plug this in, I'm going to have 2 times 4 plus 1 to the 1/2 power minus 2 times 0 plus 1 to the 1/2 power. And so 2 times 4 is 8 plus 1 is 9 to the 1/2 power minus 2 times 0 is 0 plus 1 to the 1/2 power. Sorry for my scribbling. 9 to the 1/2 power is 3. 1 to the 1/2 power is 1. 3 minus 1 is 2. So we have found a definite integral using this process, and we have an answer of 2. But remember, what we did that was the most important thing was that we put a 2 in here to complete my dx, and we balanced it with the 1/2. Alright, let's look at one more with that same idea. I'm going to rewrite this first. We have an integral from 1 to 2. I'm going to write this as x to the 3rd plus 1 to the 1/2 power. Then I'm going to write my 2x squared. Then I'm going to write my dx. Alright, so watch this one carefully. Is 2x squared the derivative of x to the 3rd power? Well, not really, because the derivative of x to the 3rd power plus 1 would be 3x squared, and this is not a 3. So let's do this. Let's take that 2 out of there by moving it over here. Remember that coefficients can go through the integration symbol. You don't have to do anything special for that. So we're going to take that 2 out, and I'm going to replace it with a 3. So now it's 3x squared, which is the derivative of x cubed. So if I put a 3 in here, how do I balance it? I'm going to come over here, and I'm going to divide by 3. So the 3 down here that I just scribbled on, it messed up horribly. So the 3 down here and the 3 over here actually balance each other. They actually would cancel out. But because we fixed it this way now, 3x squared dx that is a complete dx, which is going to go away. And so when I integrate this, I'm going to have 2/3 x to the third plus 1 was to the 1/2 power. Now it's going to be to the 3/2 power, divided by 3/2, which means over here I'm going to multiply by 2/3. And we're going to go from 1 to 2. So this is going to be 4/3 times, when I plug in 2, I'm going to have 8 plus 1, which is 9 to the 3/2 power. When I plug in 1, I'm going to have 1 plus 1, which is 2 to the 3/2 power. And part of that's going to work out to be really nice. We have 4/3. 9 to the 3/2 power, well, if you take the square root of 9, you get 3, and 3 to the 3rd power is 27. But if you do the square root of 2, you get the square root of 2, and if you do that to the 3rd power, you get the square root of 8. So I'm actually just going to leave it like that since I'm out of room. And you probably want to double check me and make sure that I plugged everything in correctly. But let's see. When we plugged in 2, we had 8 plus 1, which was 9. And when we plugged in 1, we had 1 plus 1, which was 2. So I'm going to leave this just like that so we don't mess anything up. And that's going to be the answer. That's okay. Sometimes you do get some crazy answers. Okay, so I've been talking about U substitution, but you haven't seen me do any U substitution yet. I've been talking about the process of it. So the best thing about U substitution is if you recognize the pattern, make sure your dx is complete, and then just go ahead and do your normal add 1 to the exponent and divide by that new number. Sometimes you don't have that option, and here's an example of that. If I rewrite this problem, I'm going to write this as 1 minus x to the 1/2 power. I'm going to put x squared behind it and dx behind that. And so, of course, my first question is going to be, is x squared the derivative of 1 minus x? No, it's not. The derivative of 1 minus x would be 0 minus 1. So that doesn't work at all, not even a little bit. We can't even put a number in there to make it all mathematically work out. Can I distribute the x squared in? No, I can't, because this is to the 1/2 power, so I always kind of just say, look, that 1/2 is blocking you, you can't get past it. So we can't distribute it. So now what do? Well, now we're actually officially going to use the U substitution, and here's how the U substitution works. I'm going to let U stand for the inside of my parentheses. So the U is going to be 1 minus x. Okay? Now, from here, I'm going to find the derivative of this. So I'm actually going to scoot to the next page so that you can see what's going on. So remember, I have 1 minus x to the 1/2 power. Then I have an x squared dx. Let me check myself, make sure I got it all. Okay, so if U, let me go over here on my side. If U is 1 minus x, what's the derivative of this U? What's the derivative of U? Well, the derivative would be the derivative of 1, which is 0, minus the derivative of x, which is 1. So the derivative of U is negative 1 dx. Okay? So basically we're changing things so that our x's could be represented in terms of u's. Let me show you one thing we already know. If 1 minus x is u, then where this is right here, 1 minus x, we could change that to u to the 1/2 power. That's a much simpler problem because now it doesn't have any parentheses. Now, I have a little bit of an issue. I want to make a substitution for dx, but dx over here is not by itself, so I have to divide by negative 1, and I have negative du equals dx. So where that dx is right there, I'm going to replace that with negative du. Okay, so hopefully you see the problem already. What about this x squared thing? Alright, so let me show you the cool trick that you can do with U substitution. if u equals 1 minus x, if I were to subtract 1 from both sides, u minus 1 would be equal to negative x. And if I were to divide by negative 1 all the way across, negative u plus 1 equals x. So I took this equation, I manipulated it to where the x was by itself instead of the y being by itself, and now I have something that we can plug in for x. So if I have x squared and x equals negative u plus 1, then we can plug that in like that. Now, if I were you, I would already be frustrated with this problem, because what does that help us with? That doesn't seem to have helped me in any way. Well, actually it has helped us. Let's do a couple things. This negative right here with the du, let's put it on the outside. I have u to the 1/2 times negative u plus 1 squared, but this, we know how to FOIL this out, don't we? So let's FOIL it. U squared minus 2u plus 1. Still have the du in there. Well, how does that help us? Well, can we distribute this u to the 1/2 now? Yes, we can. So the negative's still out there. When I distribute the u to the 1/2, I get u to the 2.5, which is 5/2, minus 2u to the 3/2 plus u to the 1/2 du. And now this is in polynomial form, and we can integrate each of these. U to the 5/2 becomes u to the 7/2 divided by 7/2, which we flip and write as 2/7, minus 2u to the 3/2 becomes u to the 5/2 divided by 5/2, which we'll flip and put as 2/5, plus u to the 1/2 is u to the 3/2 divided by 3/2, which we'll put as 2/3. Add a little plus c here at the end, and we actually have an answer. Now, the problem is this is not the completion of my answer, because my answer started with x's, and now I have u's. But it's called u substitution for a reason. Don't we know what u equals? Doesn't u equal 1 minus x? Yes, it does. Aren't you thrilled? So, everywhere I have a u, and I'm going to have to be really clever to get this out of here. Everywhere I have a u, I'm going to replace that u with 1 minus x. 1 minus x, 1 minus x. And there's my solution with the negative on the outside and the plus c at the end. Now, stop, rewind, watch this whole problem again, because you're probably a little bit lost. But I will tell you this. This process is used very seldom. It's an important process, but it's used very seldom compared to the processes we used at the first, where you just recognize the pattern and try to follow those steps. So, on these problems that you're going to do for homework, especially these first ones, don't be expecting to have to go through that U process. Remember that you just need to recognize the pattern, recog the pattern, and then you can make sure your dx is complete, and you can just integrate it like normal. The last example that I did is probably going to come up down here, and you just want to be very careful as you go through that problem, and of course always ask me for help.